So I'm first going to introduce you to the Michaelis-Menden equation, which is an equation we'll be looking at throughout the rest of this chapter. And it is used to describe, again, all of this is describing the kinetics of a biocatalyst, of an enzyme. So we're just talking about how the rate at which a catalyst is able to turn substrate into product. And we're also talking about how efficiently a catalyst is going to bind to its substrate to turn it into product. So all of this, again, is thinking about, it's different ways of talking about and thinking about how fast and how efficiently an enzyme is working. So this equation is going to be using new terms, which we will discuss, which is this velocity, Vmax, and Km. Now, this we should already have seen. This is just the concentration of the substrate. Now, I put this other equation down here because I want you to see an equation we talked about before, and it should seem familiar. When we talked about the Hill equation and the Hill plot, we used this equation below, which shows the ratio of binding sites, the ratio of enzyme that is bound, or the ratio of protein that is bound. Remember, this equation on the bottom is not just for enzymes, it's for proteins in general. It could be for carrier proteins. So this just shows the ratio of protein that is bound in relation to the amount of ligand. We can also call this substrate, same idea. And the KD, the dissociation constant, which is telling you how efficiently the protein binds its substrate. There are a lot of parallels between these two equations, but I want to point out that one of the main differences is the Michaelis-Menten equation is going to be relating concentration of the substrate to the rate of the reaction for a catalyst. The Hill plot equation does not ever deal with rate. And again, that's because the Hill plot equation is not used for enzymes. It's just used for proteins that bind a ligand. So it can be used for any type of protein that has something that it binds to. So again, Hill plot equation is talking about efficiency of how well a protein binds to a substrate based on the concentration of the substrate. Whereas the Michaelis-Menten equation is looking at the rate of a reaction, the efficiency of the rate of a catalyst, of an enzyme, based on the concentration of substrate. So they are related to each other, and actually you can get information from one to the other. They are interrelated, and mathematically, again, you can show a relationship between these two, but I wanted to really clarify how they are similar, how they do look similar. They're going to give us similar looking information, but they are also different. So let's continue talking about this Michaelis-Menten equation and each of these components. So again, we have our equation here, and I'm going to break down each of the pieces that we talked about. The velocity, is equal to the rate of product formation. So again, if you have an enzyme plus a substrate, they bind with each other, and then they make product. So it's how fast you make this product. This is written in terms of concentration because it's how much product is there. So concentration of the product per some time unit. That's a rate, right? How fast something is being made. So this could be concentration of a product that is made per second or per minute, just some time unit. So that is the velocity. That's what velocity is. When you see this on, it is the rate of the product formation, how fast product is being formed by this enzyme. The next component I'm going to talk about is the Vmax and the Km. So these are going to be derived from our velocity and substrate information. And I'm going to show you them graphically as I talk about them. And I want to make a point that, again, this equation is for an ideal single reaction where we just have one enzyme plus a substrate binding and making product. Sometimes enzymes have multiple substrates. There are other things happening. There's convoluted pathways in which they act. So this equation does not fit every enzyme perfectly in every reaction. And again, we'll talk about those. So again, this is the ideal Michaelis-Menton reaction for the ideal rate of an enzyme. But again, as I noted, you can have deviations in this based on things like inhibition of substrate. If you accidentally have inhibitors around, in general, this will deviate this ideal rate. So I want to spend a minute talking about how we measure this information. How do we measure velocity and then determine these other constants, Vmax and Km? If you experimentally wanted to measure these, you would take an enzyme and you'd mix it with a substrate. And in both of the cases, you're going to know how much of each you have. So you measure out 1 molar of enzyme, you mix it with 1 molar of substrate. So you know the concentration, you mix them together. And then experimentally, you would record the rate of one of two things. You could look at how fast the substrate goes away. So if you're able to see the substrate, like if it is colorful, if you have this happening, enzyme plus substrate going to this, if you measure how fast the substrate disappears, that's also related to how much product is being made. So one thing you can do is look at the disappearance of substrate. So right here in this plot in the top left-hand corner, you might get some data like this, which is the absorbance of your substrate, how much substrate is around over time. So you might see that it decreases. So you mix them together and slowly the substrate is decreasing. What that means is that product is increasing. If we know substrate decreases, product increases. Now, of course, the other thing you can do is just directly measure how much product is formed. The reason you would pick one or the other is sometimes it's just easier to see substrate and easier to see product. Sometimes the absorbance of a substrate is just very easy to record, whereas the absorbance of product might not be. If you looked at the absorbance of product over time, you would get a plot like this, right? You'd see oh, over time, I'm making more product, I'm making more product, I'm making more product. Now, eventually, your enzyme is going to stop making product, right? You mixed an enzyme and a substrate together. So if I have my enzyme here, and I mix in a concentration of 2 of my substrate over time, eventually I will make 2 of my products. And then essentially my product concentration will flatten out. That's why this graph looks like this, right? It starts to flatten out because you only put so much substrate in there, you're only going to get so much product out. So this is what your plots would look like. And again, this plot here is just measuring how much product is being formed versus the time. Now, I said that our Michaelis-Menten equation is using velocity, and that velocity is product, concentration of product over time, right? So I can measure the velocity from one of these curves. I can figure out how much product versus time is being formed. But what I want to do to look at how that changes is measure velocity or measure product versus time, but with different amounts of starting substrate. So instead of starting with 2 substrates, I might start my enzyme off with 3 substrates and then see how long does it take to make all of my product. And so what you do is you would get a plot in each of these cases. You would measure same enzyme, 1 substrate. How long does it take for me to make product? You record that plot. Enzyme, 2 substrates. How long does it take for me to make all of the product? Enzyme, 3 substrates, etc. So I'm just changing the concentration of substrate and recording the data. And again, for each case, I am getting the velocity. The velocity is this initial part of the plot, how fast the rate is going at the very initial part. And I would get that velocity, again, the slope here, product over time, at each curve. So here I would have the velocity for substrate equals 0.2 micromolar. And here I would get the velocity for substrate equals 0.5 micromolar. And here I would calculate the velocity for substrate equals 1 micromolar. That is how I generate then this plot. This is a different plot than what I was showing you here. So again, I want to reiterate, this plot here is just measuring velocity, which is concentration of product versus time. It is a rate. And it is doing it multiple times. I have to find the velocity for different ranges of substrate concentration. All of that data is compiled here. So now look at my y-axis. My y-axis here is velocity. So I got the velocity from each of those curves. And my x-axis is substrate concentration. So for example, just one of these lines gives me 1 data point on this plot. a whole curve here gives me one data point here because I get initial velocity versus concentration. And again, you have to do that multiple times. You get multiple data points, and then each of those data points give you this. This is a Michaelis-Menten plot. This graph, again, does not tell you product formation over time. That is this plot. So this is, again, explaining how we get our Michaelis-Menten plots that we're looking at. This is how we get it experimentally. This is the end product. So here we are looking at velocity versus substrate concentration. Again, what is this telling us? This is telling us how the rate of the catalyst, of the enzyme, is affected based on how much starting substrate is around. And again, you'd probably imagine that the curve is going to look exactly how it looks if you think about this. If I have one enzyme and I have one product or substrate, the rate at which it forms product will be probably pretty fast. So look at the initial velocity here. Now, if I have a lot of product around and I just have one enzyme, the rate that it will form at least one product, if I have 3 substrates around, will be faster. And that's just because there's more substrate around. There's one enzyme and now it's just surrounded by substrate. It's going to form that product really fast. So if there's more substrate, this rate increases. And again, this is just a numbers game. The more substrate I have around, the more likely this enzyme is going to be able to find some substrate, and the faster product is going to be made. Now, eventually, the enzyme hits a plateau, and you can see this happening in the graph. Why is that? Well, eventually, it doesn't matter how much substrate we have around. Eventually, at some point, the enzyme is saturated in substrate. There's so much substrate around that it doesn't matter if I add one more substrate, the rate that it forms product is going to be the same. That's what this plateau is. This is the concentration that our enzyme is saturated at. So this is the point at which it doesn't matter how much substrate is around, the rate is just going to be the same. That point, that concentration, this point at which it plateaus is called our Vmax. This is the maximum velocity, the maximum rate that the enzyme can achieve. Again, at this point, the enzyme can no longer go any faster at making product. Doesn't matter how much more substrate I put in, it is maxed out. So this is our Vmax. This is a constant. Every enzyme has its own Vmax. And again, the Vmax can be changed if you change other components that generally change catalyst and enzymes reactions. So again, inhibitors, other substrates, and we'll talk about how you change Vmax. But ultimately, for just a normal enzyme and its substrate, this is a constant. This can be determined for an enzyme based on data that we're looking at right now. So if you put together a Michaelis-Menten plot, and you look at where it plateaus, this is the maximum velocity that any enzyme could, depending on its plot, achieve. Now there's one more constant that I said we would talk about, and that is Km. This is the Michaelis-Menten constant. That's where the M comes from. So Vmax is a velocity. That means its units are some concentration over time. Again, it's the maximum rate that an enzyme can ever go at for that enzyme. The Michaelis-Menton constant is just a concentration. So I'm going to say this is a velocity, this is a concentration. The Michaelis-Menton constant is the concentration at which you have hit half of your velocity. This constant is just used as a way to help us understand the efficiency of a enzyme. So it's relating the actual substrate concentration, how much substrate has to be around for it to go at its maximal rate. It's kind of giving you an idea of that. And similar to our KD, which is a different constant, similarly, the lower this constant, the smaller this constant, the more efficient the enzyme is in this case. So it's more efficient at binding and catalyzing a reaction if you have a small Km. So again, this constant helps you relate the concentration of substrate you need around to achieve a maximum velocity. So again, here is the plot that you would see, a Michaelis-Menten plot, and how you would derive the information from this plot, those constant, is shown exactly. So you can see that our velocity is always going to start off as being semi-linear, and then it plateaus at this point, which is the Vmax. So the velocity at this plateau is what we call Vmax. That's how you can determine Vmax from a Michaelis-Menten plot. And the Km is wherever, if you figure out where your Vmax is, figure out where the halfway point is. So the half point of Vmax, and then go over to your x-axis and go down. And wherever the concentration is there, that is your Km. So I want to talk a little bit more about distinguishing these Kms, and we talked about Kd, and there is one more unit that will be brought up, which is called Kcat. I want to talk about how these are different and what they mean exactly. So Km you just saw is related to enzyme kinetics, and again, it is equal to the amount of substrate. It is a concentration of substrate where the reaction rate is at its half maximum. So concentration at which a reaction rate for an enzyme is at its half maximum. And it measures, it gives you an idea of the affinity for a substrate to its enzyme. Again, if this is lower, the lower the Km, the more affinity the enzyme has for the substrate, because you just need less substrate around for it to react at a fast rate. So if it has good affinity, you need less substrate for the rate to be faster. Kd, remember, is related to just protein binding. It is not related to enzyme kinetics. It's not related to rate. It is also a concentration. It is the amount of concentration at which half of the enzymes present are bound to its substrate at an equilibrium. So this just tells you the point at which half of the enzymes are bound, not the rate at which they are converting things. And again, you can use this for just proteins that aren't enzymes. It's just telling you how well a protein binds to a substrate. Now, are these giving you similar information? Yes, they are. Generally, Km and Kd are going to be similar. If one is low, the other is probably low, because if something binds onto its substrate really well, which is the Kd, if it binds it really well, that probably also means that it doesn't need a lot of substrate to get a high rate, because the affinity for the substrate and the protein are both strong. Now, again, these are both concentrations. The value, the units that these are measured in are concentration. There is one more constant we will talk about when talking about enzymes, and that is called kcat. This is also referred to as the turnover number. This is not a concentration. This is a rate. This is the number of times each enzyme site converts substrate to product in some time period. So again, it's how fast an enzyme turns over, or how fast it is able to take substrate and make it into product per some time unit. The number of times, so it might be like this enzyme did a conversion twice in a minute. That would be a kcat. So number of times the enzyme works, the number of times an enzyme does its job per time unit, per minute. So again, this is going to have units that are going to be what we call inverse time. So this is some number, like the number of times it does its job over a time unit. And again, this could be minutes, this could be seconds, this could be hours. So this is measuring another way to talk about efficiency of an enzyme, but using a different unit. Here you can see the relation of the two together. You'll notice that if you have a high kcat, so you have a high turnover rate, that means you are a very efficient enzyme. So a big number for kcat means that you turn over product very fast. Remember, Km, the Michaelis-Menton constant, is a concentration, and the lower it is, the more affinity you have for your enzymes. Now, lastly, you will sometimes see a final way to express enzyme efficiency and specificity, which is kcat over km. So this is taking its efficiency, how rapidly it works, which is kcat, and it's taking its specificity, how well it binds to its substrate, and it combines the two pieces of information to get one number. So here, if you have a high kcat and a low km, your kcat over km, the combination will be very high. So for example, kcat was 10 to the 4th here. Km was 10 to the -5th, that's small. And you can see when you do kcat over km, you get 10 to the 8th. So when the kcat over km is high, that means both things, the efficiency and the specificity, are very good for this enzyme. So again, want to highlight that this KCAT is specificity and Km is, oops, excuse me, I just got that backwards. KCAT is its efficiency, how efficient it works to turn over, and Km is its specificity. Okay, so now we've described the Michaelis-Menton plot, this hyperbolic looking plot that helps you get information about the rate of an enzyme, and it's used to calculate an enzyme's Km and its Vmax. So again, the maximum velocity, the maximum rate that it can ever achieve per some substrate, and the essentially its specificity for its particular substrate, the concentration at which it is effectively making the product. This kind of information can easily be taken from a Michaelis-Menton plot, which is what we just went over. There is a different style of plot that takes the same information, but it graphs it differently. This is called a linearized double reciprocal plot. It also sometimes is called a line Weaver-Burke plot. So you'll see it described as this as well. This type of plot, again, same information, just it's graphically visualized differently, is good for variations of a type of situation where you have maybe two substrates instead of one substrate, or you have an inhibitor.